Assalamu alaikum everyone, how are you? So in this video, we will design a textile based reflective metasurface for around 2.5 2.4 gigahertz applications. So let's begin, starting with the settings, all the settings that you know, and just cross check everything. So click this as well, so you can automatically see the reflectance, transmittance and absorbance. It's better to do with the frequency if you want to see the results in the frequency domain. And let's begin. Okay, we will be using a material felt type material that is not automatically like in the libraries, so we will define it extra, so you'll see that way as well. So let's begin. So around 36. This is we do for like symmetrical designs. So both ways, here is the origin, go like this in x-axis and then y-axis. So it's a much symmetrical, and for substrate I just in the downward direction I go, so I can just work on the top, and the ground is mostly all ground for reflective type of meta surfaces. So let's the thickness is 8 mm and till 0 let's I will just say the felt. You can see the different properties, and you can see it's not automatically available. So click on new material. I will say felt textile substrate. You can click on this, so that is available in the material library for the future versions of the work you do. You can define other properties. Let me just change this value. Give it a value of 1.25 and tangent delta is 0.05. Okay, so other properties are also, but these are the major properties I have in this regarding. So I will click on this, click apply and click OK. So let's see. Okay, this is it. I will just do one thing, working plane, remove the working plane and bonding box, so it is much more easier to see and work on. Now let's make the ground the same as the substrate, but with different thicknesses of height. Oh, one mistake I did. 36. Okay, so now we have to go -8 and -0.035. That is the copper cladding, or whatever you have, you can just change it. It doesn't matter much. But and here you have to select the copper. You can select PC, and better is to for actual similarity to the actual result, you just select copper and yield. So you can see it here. Okay, so I will just try to the design grid involves a lot of steps, but I will use the mirror function to just make it much easier. So we will just go patch, more like a patch. So from 0 to what we have to go till like 32 divided by 2, 0 to 32 divided by 2, 0 to 0.035. Let's see how it's okay. So it is, I have to cut here. There's a cut here as well, so I will just, after this I will use always better to see that you are doing correct by just checking out the design. The more you design, the more fluent you begin in this cut. Okay, so 32 by 2, you have to go like there, and from there you have to subtract -2 and maximum 32 by 2. Okay, so you come like here, and then there is a cut here to the x. Same as with the y. X is actually here, but when I just give it a top, so it will just move to a better place. Let's see if there is any mistake. We will see, because we are previewing it. So here, so now I'll just do the vacuum. So I can use the vacuum and cut it here automatically, or I can use the Boolean function. So I will use the vacuum and then cut it out cut away the highlighted part. Okay, there are many ways to do it. Okay, so now as I have made a symmetrical design, so I have just to replicate it. First of all, I will replicate I can replicate in any direction, and then let's see X or Y, and then we can just replicate it, copy it in the X. Let's see, preview, always preview, so don't make mistake. And if I don't press the copy, it will just shift here, and here it will be vacant, so I have to press the copy and I click apply. So I have okay, it's done actually. I will just, so now I click on these two and click on the transform mirror and copy, and now in the Y direction. So it comes like here, simple, clean. So you can leave it here like this, or you can just boolean add them all, so it looks like a much clean version. And let's see, simulation I can just do from 1 to 4. The response is like, okay, what happened here? 1 to 4 gigahertz. Yes. Did something bad happen or what? Okay, the bounding box was hidden, so that's why I was just curious, where did it go? And one more clarity, for most of the cell you have this, because at the backside is the ground, it won't have any effect, so it will be extra simulation and time, so it's better to do it so it is a conductive. Just checks its boundaries to conductive, automatically takes the result from there. And in upper Z you have to just, the maximum dimension, that is 36 for good phase adjustments. It doesn't affect much, but it's better to do here as well. So that's it. Let's start the simulation. One more thing, if you just want to just change up color, you don't like there are a lot of features in CST, the more you use it. So I'm just sharing this so you just learn as well. Just make it like something like here. Looks odd, but let's begin. You can play with your favorite color. So let's start the simulation. So on the top it is a copper patch, and in between there's a textile based substrate. It can be any, you can define it. I told you the procedure. You can put in the different values according to your need, according to your checking out the different data sheets, or from different papers you can check out what they are using, or from the different data sheets from manufacturers, the material characterization reports. So that's how you see these all results. So if you ever have any query, you can comment here, or you can mail me, or in future if you want to collaborate for any work, you can share on my email. I will try to respond you if that area is my good area as well, so I will just try to collaborate. Any problem you have, you can share. If I have the solution, I will just try to if you have issue in any paper, anything you cannot just clear, you can share with me, and I will just try to design that as well. Let's hope. Actually my laptop is not on charging, so maybe it just happened a little faster on the simulation machines. Okay, these are simple designs, so they are good on your laptop. That's okay. But if you just do very long simulations on your laptop, battery is another, and you don't have good cooling systems, so it may get affected and get slow. So it's better to use on the CPUs or other simulation systems, PCs having good RAMs and CPU, so that works better for you. So rest is this. Okay, now I designed with non-parametrically. So if you design with parameters, you will get the values of parameters here. Like in 36, I can just say the width and length, etc., and it will show itself there. So you can, if you just know the operating frequency, you can just change it. Like it was around 2.5 or 2.4 gigahertz, so I just gave it 1 to 4. So maybe it's just taking a lot of time. I could have given from 2 to 3, and I could see my results easily. So Like these are the, I think it's done. The steps you can do to just, even I can put the PC here so it will take less time to simulate. Let's see the results. Okay, so here you see it is less than minus 3 dB, that fulfills the criteria of the reflective nature. It is symmetrical, so it is TM and TME mode both are same symmetrical unit cell, so it gives both polarization, work for both polarization. This value is far less than any, like there is no, almost no like minus 65 dB or lesser transmission, nothing it can transmit because the backside is reflective. So that's it. So that's it from my side. If you want to see more videos, you can subscribe to this channel. And the problems you have, especially related to meta surfaces, reconfigurable intelligent surfaces, frequency selective surfaces, anything like that, active or passive, you can share with me. And good luck. Take care.